This is the story of our rain garden at NIE. Rain gardens are one example of what is known as low-impact development technology. Other examples of low-impact development technology include green roofs, grass swales, porous pavement, rain barrels, and even planting trees. Low-impact development technology works with nature to manage the volume of stormwater runoff and reduce localized flooding, as well as improving the quality of stormwater runoff. This video begins by discussing the general principles of rain garden design and then shows the steps of the design, construction, and monitoring at the NIE rain garden. Let's begin our journey. A rain garden like the one at NIE will be constructed using several different substrate layers, as shown here. Different types of plants also are included to help remove nutrients, maintain infiltration rates, and protect the substrates from erosion. The stormwater runoff flows into the rain garden where it is stored at the surface and then gradually infiltrates through the substrate layers. The process reduces the rate at which runoff reaches the storm drains and therefore also reduces the risk of localized flooding. This figure shows a hydrograph for a small river or drain under different land use conditions. The blue line indicates the hydrograph expected for a storm if the land around the drain is relatively natural, with lots of forest and parkland. The tan line indicates the hydrograph expected for the same storm, but with a more typical urban land use of roadways, buildings, and concrete. The water no longer can infiltrate and be stored in the soil. Under this situation, a greater volume of runoff reaches the drain more quickly because of the impervious surfaces, and this results in a higher and earlier peak. As such, there is greater potential for localized flooding. The green line shows how low-impact development can work. By infiltrating and storing water, low-impact development technology gradually releases stormwater runoff to the drains, thereby reducing the peak flows. In the example of the NIE rain garden that we see here, there's a special 100 mm deep anoxic layer just below the upper loamy soil filter media. This anoxic layer is created through a mix of mineral substrate and wood chips. As the wood chips decay, the layer becomes reduced or oxygen deficient, and this enhances the process of denitrification. Denitrification removes nitrate, or NO3 negative, and nitrite, NO2 negative, that are constituents of the infiltrating water and transforms them into nitrogen gas that can be released to the atmosphere. A reaction could look something like this. In this case, the CH2O is a generic carbon source that is represented by the wood chips. In addition to the anoxic layer providing a level of treatment, the plants and substrates will filter and absorb suspended solids and associated nutrients and other contaminants. The roots of the plants will take up nutrients and contaminants, and these will be locked in the biomass that will be removed upon harvesting. The infiltrated water in the NIE rain garden collects in the underdrains, which are 100 mm diameter perforated plastic pipes that run parallel to each other at the bottom of the rain garden. The water then leaves the NIE rain garden through a collection sump and then onward to a nearby drain. Rain gardens can have two different designs to drain the water. The simplest and least expensive design is known as a soak-away rain garden, where the water simply continues to infiltrate downwards out of the rain garden. This design can be implemented if the soil percolation rates are sufficiently high. If percolation rates are too low, then the rain gardens must be designed with an underdrain to move the water away and avoid rain garden saturation and ponding. So, in conclusion, we can see that the rain gardens have a dual purpose of managing stormwater runoff volume and also providing a level of treatment for the runoff. Let's now take a look at the process behind the construction of the NIE rain garden. The NIE rain garden was constructed as a partnership between PUB, AECOM, Green Earth Consultants Limited, and NIE. The first step in the process was to determine where the rain garden should be constructed. Based on campus visitations and surveys, a total of 7 candidate sites initially were identified. As we see here, preferred sites were then identified based on further site inspection and a scoring framework. Included in this scoring framework was an assessment of the soil percolation potential, catchment area, catchment slope characteristics, visibility to the public, presence of utilities that might require diversion, and potential for interrupting school schedules. Site 7, an open grassed area between the art gallery and the playhouse, ultimately scored the highest and became the selected site. While AECOM was conducting its site assessments, a parallel assessment was done at Site 5 as part of the third-year Ecosystem Dynamics class in the Geography program at NIE. The students identified catchment area, measured slopes, analyzed organic content and texture, and determined infiltration rates. The students were asked to determine, based on their investigations, whether Site 5 was suitable for a rain garden. While most concluded that the physical characteristics of the site were suitable, a number of students noted that it was a less desirable site because it was not a high-traffic area or readily visible. Shortly after the students completed their assignment, Dr. Stephen Tan, the lead from AECOM in designing the rain garden, gave a lecture in class about rain gardens and PUB water management philosophy. Students were happy to see that many of the same tests that they applied in their test site also were used by the consultants. Once the preferred site was selected, the NIE rain garden design began in earnest. Because of the soil characteristics, it was determined that an under-drain design was appropriate for this site. The plan view of the rain garden design, showing the bottom layer, can be seen in this diagram. The dashed black lines indicate the location of the two parallel underdrains that eventually join near the collection sump. Here we see the selected site before construction began at the end of September 2016. The AECOM team can be seen digging a small pit to assess soil percolation rates. This is the landscape architect's vision of what the site was to be. Now, let's see how the vision became reality. The official handover of the rain garden occurred on February 1st, 2017, with staff from PUB, AECOM, Green Earth Consultants, and NIE attending. A new batch of students in the Ecosystem Dynamics class also attended, as their first assignment became the first post-construction evaluation of the rain garden. Students were asked to identify the plant types and why they were placed in certain locations. They measured infiltration rates, and they also analyzed the texture for different substrates. Subsequently, fourth-year students are conducting water budget studies and nutrient mass balance studies in the rain garden. These studies are aided by an IoT meteorologic and flow monitoring station. Preliminary results for suspended solids and nutrients show that the rain garden is effectively improving water quality going to the drain. The NIE rain garden already has provided benefits to the environment, and it offers a unique opportunity to conduct long-term monitoring of performance. This information will help inform future designs and maintenance practices. The NIE rain garden also is a wonderful resource that helps enhance eco-literacy at all education levels and allows students to participate in an innovative and eco-friendly approach to water management.